Here the problem is joint time bandwidth optimization. So a simple problem of this type would be, let's say you have a pulse of some length t, ft, and we'll say that its energy is 1 or some quantity. So this is, and it says it's a Fourier transform gives you the distribution in frequency, what goes on in the frequency domain. So let's say it's a Fourier transform f of omega is like this. So what we mean, if it is a pulse here, then the transform is not going to be a pulse. It's going to be all over the frequency domain. But we want this energy to be maximized in some frequency band B naught. So we want the maximum of the energy there. So if you look at the total energy, so the goal is to maximize the energy within this band. So energy is going to be this quantity, square of f omega squared. So I'm going to call this EB naught is f of omega squared d omega. I want to maximize that quantity by selecting the pulse. So the only restriction on the pulse is that it is a pulse of length t, and the shape is free. That's the only freedom we have. Its energy is fixed, because otherwise you can boost up the energy there and boost up the energy here. So that doesn't make any sense. We'll start with some constant energy in the time domain, and we want to pack more. We want the shape of the pulse where most of it is packed in some frequency band. It doesn't have to be around 0. It could be somewhere here, but it's as good as it's just a translation. Also, to make further progress here, I'm going to introduce this function, a unit rectangular function in the frequency domain of height 1. So of course I can write this as minus infinity to plus infinity. Advantage is when I bring in that function, I can write it like this, because h omega squared is 1 only from minus b naught to b naught. So since this, let me put a 1 over 2 pi here. It will be just a constant. But so this I can write this as minus infinity to plus infinity f omega h omega squared multiplied by f star omega. So I can use Parseval's relation because it's of the form a or q, some q omega f star omega. So that's in the frequency domain. So in the time domain, that's minus infinity to plus infinity qt f star t dt, where qt is of course the inverse transform of q of omega. qt is the inverse transform of this. So that's going to be ft convolved with the inverse transform of h omega squared, right? Fourier inverse of h omega squared. This function is easy because this is 1 over 2 pi minus b naught to b naught 1. H omega squared is 1. E raised to j omega t d omega. So this is so this would be e raised to j omega t over j omega 1 over 2 pi. So minus b naught to b naught. So that will be 2j sine b naught t. 2j cancels. Remember, this is the inverse transform, so this is going to be integration is in omega. So the result comes out to be 1 over pi sine bt or b naught t over t. So I can multiply by b naught here. So I get this. So this is sinc bt. So qt is going to be ft convolved with 1 over or b naught by pi sinc b naught t. But remember, ft is now a short pulse. ft is a pulse, so this is integral from 0 to t, qt ft dt. By Schwarz inequality, this is going to be less than or equal to q squared t dt multiplied by f squared t. This is 1. And we know this, we of course want to maximize this quantity. So this quantity's bottom line is less than or equal to this quantity. So if you want to make that quantity equal to the maximum, so this is the maximum value. So we want to make it equal, we know that these two functions have to be proportional. So this is maximized. So EB naught is maximized if and only if Qt is proportional to lambda ft. But Qt is the convolution of here. Qt is here. So Qt is going to be the convolution of ft, and so that's going to be sinc b naught t minus tau multiplied by f tau. Tau goes from 0 to t. So we have to solve this equation, integral 0 to t sinc b naught t minus tau multiplied by f tau d tau. Will be lambda multiplied by, this is the equation that to be solved. So this is a classic prolate spheroidal function. You can do a little better here, because if you redefine new variables b naught to t equal to x and b naught tau equal to, let's say, u, and so you get this expression comes out to be, notice that when and tau also, so when tau is t, the u goes to, when tau is 0, u is 0, when tau is t, u goes to b naught t. So this expression reads now b naught t sinc x minus, let's say this is u or y, whatever, x minus y. Then t is not, notice that tau is y over b naught. So this is f of y over b naught. D tau is dy over b naught. So that's a constant. That constant we can absorb with the lambda. So I'm going to change the lambda to mu. In fact, lambda also absorbs this other constants, which is here pi over b naught, etc. And here you have f of t is going to be x over b naught. So if you scale the f by b naught and call it f tilde, then this expression is, you can rewrite it like this. So in other words, or let me leave it, I'll write another expression. So for example, so finally you can rewrite that expression as integral 0 to b naught to t sinc t minus tau f tilde of tau d tau equals f tilde of t, where t is now from 0 to t over b naught, a normalized duration. We notice that t, when t becomes, right, b naught t, when you multiply it by b naught, right, so t, the new variable is x. X is going to be b naught t, so if you multiply by b naught, b naught, b naught, b naught t is x. So this would be f tilde is actually, this is what I'm going to call f tilde of x. So x, which I, instead of x, I rewrote it as t. So the bottom line is here it is. So interesting thing is, for this specific problem, if you're just trying to maximize the energy within this band B naught, this equation need to be solved. So this you can discretize it and solve it as Ax equal to lambda x, right? Where A is going to be the discretized values of this with the diagonals 1. And so the x will turn out to be the solution you're looking for, which is the, and you want to maximize it. That means you want to choose the solution corresponding to the largest eigenvalue. And that's going to be, these are going to be the prolate spheroidal functions. But the interesting thing is, this only depends on the time bandwidth of product, T and B naught. So given T and B naught, we can solve, and the solution is going to be unique.